Everybody, welcome back. So today we're going to be talking about the dot product and the cross product, two sort of vector arithmetics that we can do to obtain certain things. Now, before we get started, I want to mention, sorry about the last video and the weird noise that was happening. So I was using the mic on my computer, but my computer was overheating because I was recording, and so what you hear is that like the fan's going. So I decided to switch to my headphone mic, and hopefully that'll fix that problem. In any case, let's go ahead and get started. So we're going to first talk about the dot product. Now, the dot product is something that we can define on any dimensional vector. So we'll just say u and v. Let's suppose that they have dimension n. Okay. Now, to do the dot product, you need to have the same dimensions. Once you have two vectors of the same dimensions, then you can define the dot product in the following way. So basically what we're doing here is we're multiplying like coordinates and then adding up whatever we get. Okay, so u1 v1 plus u2 v2 plus yada yada yada, un vn. So for example, let's say my vector u was 1, 2 and my vector v was minus 8, 4, then the dot product of this u and v is equal to, so we multiply the same coordinates, so 1 times minus 8 plus 2 times 4. Which will give us minus 8 plus 8, which is equal to 0. And we're going to see this actually means something, but we'll get to that in a little bit. Now, the dot product has a lot of nice properties. First of all, it is commutative. Okay, it does not matter what order you do a dot product in. U dot v is equal to v dot u. We have a distributive property. So if you're taking the sum of two vectors and then you dot it with w, you can distribute w, there should be a dot product there, inside that sum. We have a scalar property. We can pull scalars out of a dot product, which could help with the calculation. And we also have this other nice property, which is the length property. At least that's what I'm going to call it. The dot product of a vector with itself is actually the square of its length. Now, one thing I want to mention too, notice I'm dropping, in the last video I used this as the notation for length, but it gets kind of cumbersome as we'll see in the next result, but I'm just going to use just single vertical bars for length now. But in any case, if you take the dot product of a vector in itself, you get the square of its length, which is a super, super helpful property. Now, geometrically, the dot product gives us a nice piece of information. It actually enables us to calculate the angle between two vectors. So if we have the, notice my picture here in the upper right, if we have two vectors u and v, then we say that the angle between them is the angle that's between 0 and pi, that's literally between them. Okay. Now notice I drew it so that this angle is acute, but we could have something like this, where there's our u and there's our v. And so the angle between them in this case would be an obtuse angle. But in any case, the dot product actually gives us a way of calculating what the angle between two vectors is, and it's given by this formula right here. So the dot product of u and v is actually equal to the length of u times the length of v times cosine of the angle between them. Okay, so let's look at an example. If u is the standard basis vector, I, in R2, and v is this vector, okay, then we'll go ahead and calculate what the angle between them is. Now, hopefully you guys recognize v is actually, if you look at the coordinates, is actually a coordinate on the unit circle. So if you're really good with your trig, you should expect, and it's actually sitting right here on the unit circle, you should expect what this angle, what this angle actually is. But I'm not going to spoil it yet. But for those of you that are good with your trig, you should recognize that. In any case, let's go and calculate this angle. So cosine of theta, so we're shuffling around our equation up here. Cosine of theta is equal to u dot v. So what is u dot v in this case? It's 1 times square root of 3 over 2 plus 0 times 1/2 divided by the length of u. The length of u is just 1. The length of v, put parentheses around that. The length of v is equal to square root 3 over 2 squared plus 1/2 squared And let's simplify that a little bit. So on the top, we're going to get square root 3 over 2 divided by, now if you add this up, what you'll see is that you'll get 1. So we just get square root 3 over 2. So this means that cosine of theta is square root 3 over 2, which if you take arc cosine of both sides, that means that theta is equal to cosine inverse of square root 3 over 2. And again, knowing your trig or using trig or unit circle or what have you, we'll get that this is equal to 60 degrees, or in radians, pi over 3. So in any case, the dot product, notice the dot product is allowing us to figure out the angle between a vector. A couple of other things that result from this formula here. Firstly, and this sort of it allows us to get away from the calculations that we just did in the other problem, but you can sort of tell how big the angle is just from the dot product. So from the equation that we have up here, and I mean this one right here, right? We notice a couple of things. If the dot product is positive, which would make this equation here positive, that means that cosine has to be positive. Now, when is cosine positive? Well, cosine's only positive in the first quadrant. So if you have that the dot product is 0, that means that the angle between them is acute. So we have that picture that I drew earlier. If you have that the dot product's negative, okay, that means that this equation here is negative, which means that cosine must be negative. Now, when is cosine negative? Cosine's negative in the second quadrant. So if the dot product's negative, we know that the angle between them is obtuse. Okay, it's bigger than 90 degrees. Now, if the dot product is 0, okay, that means that this equation is 0. And how do you get that it's 0? Well, that means that cosine had to be 0. Now, what angle is cosine 0 at? It's at pi over 2. Okay. Now, what does that mean for us? Well, that means that geometrically, you have perpendicular vectors. Okay. So if u dot v is 0, that means that they meet perpendicularly, and we also call them orthogonal vectors. U and v are orthogonal. Another thing the dot product allows us to do is something called project, or projections. And I'm going to sort of go through this step by step with you guys. So let's say we have two vectors u and v, like I've drawn here. U is this upper one, v is this lower one. And let's say we want to project u onto v. Now, what I mean by that is, think about u's shadow on v. Okay, u's shadow on v would be a vector that's lying on v, but that's under u, right? So this is sort of its shadow. So this vector here is what we would call the projection of u onto v. Okay, that's what that notation means, projection of u onto v. And then this vector here, if we want to make a right triangle that goes up to u, we call this the orthogonal projection. I think your book calls it this projection, and then they put a little perpendicular sign. Okay, but we would call that the orthogonal projection because it's perpendicular to v. But in any case, the dot product helps us figure out what this vector is. And I'm going to show you guys how that happens. Okay. So let's say we want to figure out what this vector is. Notice that this vector is lying on v, right? So if we take v, okay, really what we want to do is we want to scale v. We want to take it from being this length and then make it this length. Okay, now how do we do that? Well, if you guys remember from a couple classes ago, we can always make a vector a unit vector by dividing by its length, right? So first thing I'm going to do is I'm going to divide by the length of v. Okay. And notice, by the way, I have our formula down here so you can follow with that. So now this is a unit vector. Okay. So we just have to multiply by the length of the projection here and we're good to go. That's going to give us the projection vector. Now, how do we get that? Well, we use SOHCAHTOA. So let's call this angle theta. We know that the length of the projection, I'm going to write over here because I'm losing space. Okay. By SOHCAHTOA, or the cup part, is equal to cosine of theta times u. All right. And the way I'm getting that, by the way, remember cosine of theta is equal to adjacent over hypotenuse. And what's the adjacent in this right triangle? The adjacent is the length of the projection. The hypotenuse is the length of u. Okay. So the length of the projection is really just cosine of theta times u. Okay. Now, if we use our formula, so we don't want really trig functions here. We want to get this formula with the dot product. If we use our dot product formula up here, okay, the dot product is the length of u times the length of v times cosine of theta. We get that this is really just the dot product of u and v by doing some shuffling, divided by the length of v. Okay, so that's what this quantity here is. And don't forget, we also had this quantity of v here. Okay. And remember, what's the length of a vector squared? That's the dot product. So that's how we arrive at this formula here. So that's what we call the projection, or the shadow of u on v. Another thing your book defines is comp u on v. That's just the length of the projection. But in any case, here's another geometrical result of the dot product. It allows us to project vectors onto others, or sort of calculate the shadow of a vector on another vector.